All right, so another type of filtering that's really common in graphics is called anisotropic filtering. And let me explain what the problem is and why we need something different. So imagine you have this scene. This is a floor. Okay? Now what's happening here, you can see, is that because of perspective projection, the x dimension, it reduces as you go, but the z dimension, it really flattens out to a skew angle. And the more skew it is, the worse you get this problem. So if you think about a pixel, or a patch, or region, it's kind of, it's kind of like that, because you get that real skew angle in this direction, but in the x direction is not as skew, right? In this direction it's not skewed, in that direction it's really skewed. So in this case, we kind of want more x resolution, right? And less y, because of perspective. So let's write this out. So on skewed surfaces, we might need different levels of interpolation. In x and y. I should probably not say x and y. I should probably say in u and v. Let's fix my notes. Okay, so how do we do it? Well, the solution to this problem is anisotropic filtering. And what that does for us is it lets us solve that problem by actually having an uneven sample window. So we have an uneven sample window to match this projection. Of the pixel. Okay, and we can calculate that based on our knowledge of the coordinates of the corners of the patch. Okay, and we can do that. We can interpolate that when we're doing the surface in the same way we interpolate other features. So that's our solution. So what we do is we take if this is our texture, our map at some level doesn't really matter. Previously, we'd take this this pixel, and we'd come down here and we'd do our 2x2 thing. But what we do now is we've realized, we kind of need more resolution in the x direction. So let's add on some extra pixels here, and let's interpolate broader and build those in. So this is called anisotropic anisotropic 2 times, right? So what we get is what we get is an 8x2 8x2 window. That's not right. 4x2. Yeah, okay. 8 pixels total. Yeah, I knew I was confusing something. Good. So anisotropic 2 times gives us a 4x2, or 8 pixels total. We doubled the sample space. And when you set this setting in an engine, you can do 4 times, which is 4 times the space. So 2 times the space is a 4x2. 4 times the space would be an 8x2, and so on and so forth. And you get a bigger patch as you go. Okay, so let's look at this in some slides. It's probably best to explain it visually. 36, 37, 38. Cool. So here's an example of the problem. So here's trilinear filtering on a floor. And as we go in, this is nice and mip-mapped, and so it has this nice transition, trilinear. But what you're noticing is a banding in the x direction, because even though we have sufficient resolution in the z direction, we're choosing a minification, our mip-map level based on the minification, and we end up with not enough resolution in the x direction, so x becomes blurry faster. If we put on anisotropic, then we balance that with more x resolution than we get in the z, and we have that non-square patch. We pull it out sideways to match what the demands of the scene are. So it's not equal because it's perspective, and it's not equal. Here's another example. This is trilinear, so this is no anisotropic. This is just mip-mapped. and you see the resolution on the floor is just gone. It's just completely gone after it's close. As soon as it minifies, it's gone. But in the 4x and then in the 16x, you really get this detail back because it's doing the skew angle correctly. The last thing I'll mention is that you can actually pre-compute these into a like a MIP map. They call it RIP mapping. You can pre-compute them and use those to save some computational time, but that's kind of beyond the scope of this course, but I did want to show that. All right, so that's all I'm really going to talk about for filtering, and so we've finished the filtering section of this unit.